Hello students, in this lecture we will discuss the basic concepts of probability and random variables. These concepts are essential to build up the theory of statistical signal processing. We start with probability basics. To define probability, we need a sample space S with the elements called the sample points. An event A, which is a subset of S, A is a subset of S. We are illustrating this with an example. This is, suppose this is the sample space and it has 4 sample points S1, S2, S3, S4. These are the sample points. Now, probability PA can be assigned to A satisfying 3 axioms. Number 1 is P of A is greater than equal to 0, probability is always positive. P of S is equal to 1, probability of the sample space is always equal to 1. If A and B are disjoint events, P of A union B is equal to PA plus PB. This is the third axiom. So, it says that if two events are disjoint, then the probability of their union is the sum of their probabilities. To have a more consistent definition of probability, the third axioms need to be modified. However, for that we need the concept of sigma algebra, therefore, we will not discuss that form of the third axiom here. So, we have defined probability. Now, let us see what is conditional probability. Suppose A and B are two events such that P of A is not equal to 0. Then the probability of B under the condition that event A has occurred is called the conditional probability of B given A. So, it is defined by probability of B given A is equal to probability of A intersection B divided by PA. So, what is the probability of the intersection of A and B? That divided by PA, normalized by PA, that will give us the conditional probability. Similarly, we can define probability of A given B. From the definition of conditional probability, now we can find the joint probability. P of A intersection B is equal to PA into P B given A, and that is also equal to P of B into P of A given B. Events A and B are called independent if P of A intersection B is equal to PA into PB. In the case of independent event, the joint probability is product of the individual probability. This is a very important concept, independence. What does it imply? It is a property of probability, that probability of joint event is the product of the probability of individual event. Total probability theorem. Total probability theorem is one of the most important theorems in basic probability. Let us state this theorem. Let the events A1, A2 up to An form a partition in S. So, what is partition in S? It means that S is equal to union of all these Ai's, and Ai and Aj are mutually disjoint. So, Ai intersection Aj is equal to phi for I not equal to j. Then for any event B, if we have a partition, then for any event B, probability of B is equal to sum I going from 1 to n of P of Ai into P of B given Ai. Let us illustrate this. Suppose this is my S and I have these events A1, A2 and A3. So, A1, A2, A3 forms a partition in S, okay, because A1 and A2 are disjoint, A1 and A3 are disjoint, and all events are disjoint. Now, you consider any event B. This is the event B. Now, the probability of this event B is equal to the sum of the probabilities of this event, then if I consider this event and then probability of this event. So, that way probability of B is equal to probability of this event is probability of A1 into probability of B given A1. Probability of this event is equal to probability of A2 into probability of B given A2 plus probability of this event, that is equal to probability of A3 into probability of B given A3. So, this illustrates the total probability theorem. Now, we go to one of the very important result, what is known as the Bayes rule. Suppose the events A1, A2 up to An form a partition on S, we know what is a partition, and Pai is not equal to 0 for I is equal to 1 to N. So, each of these probabilities are non-zero and these probabilities are called a priori probability. We know these events A1, A2 up to An and their probabilities also, that way these are a priori probabilities. Then for any event B with Pb, probability of B greater than 0, we can write P of Ak given B. Suppose this event B is given, then what is the probability of this prior event Ak? Probability of Ak given B, and this by definition is equal to probability of Ak intersection B divided by Pb. Now, we apply the total probability theorem here. So, this Pb can be written in terms of the a priori probabilities and the conditional probability by this sum, and similarly this intersection can be written in terms of the probability Pak into probability of B given Ak. This is true for k is equal to 1, 2 up to n. So, this probability is now the a posteriori probability. A posteriori probability or posterior probability, and it has extensive use in the estimation and detection theory. We have Bayesian estimation theory, we have Bayesian decision theory, and we will be discussing Bayesian estimation theory. With this concepts of basic probability, let us go to define random variable. Random variable, it is abbreviated as RV. A random variable x is a function from the sample space S to the set of real number R. So, actually it is a function, it is a mapping from the sample space S to the set of real numbers R. Thus, x is a mapping from S to R. So, since it is a mapping, we have to define what is the domain, S is the domain, and the range Rx is a subset of R and given by Rx is equal to Xs such that S belongs to S. So, those points are on R which has a corresponding point in S. So, these points constitute the range. So, we know what is the domain, domain is S, range is Rx which is a subset of R. We use an uppercase letter to denote random variable and a lowercase letter to denote its value. Thus, Xs is equal to A means that X is the value of a random variable X at a point S. Argument S is usually omitted and we simply write X is equal to small x instead of Xs is equal to small x. So, we have defined random variable, it is a mapping from the sample space to the real line. Now, how to describe probability in the real line? So, we will define cumulative distribution function CDF. This CDF, also called the probability distribution function of a random variable x, is defined at a point x belonging to R as capital Fx of x, that is the CDF, is the probability of those sample point S such that xs is less than equal to small x. So, we have to consider all S for which xs is less than equal to small x. So, that in that sense it is a cumulative probability, and instead of writing this symbol, we write simply probability of x, capital X, less than equal to small x. This is the CDF. So, since it is a cumulative probability, if we plot it, if it is a sample space is finite, then we may have this type of CDF, staircase type of function, which has maximum value 1 and minimum value is always 0. Similarly, we may have a continuous CDF function where x will be ranging from minus infinity to plus infinity. And we also observe that this CDF here CDF is a non-decreasing function. Also note that Fx of minus infinity is equal to 0 and Fx of plus infinity is equal to 1. CDF is a complete characterization of random variable x, and any probability involving the values of x can be obtained from Fx of x. Particularly, suppose for x2 greater than x1, suppose we are interested to find out the probability. What is the probability that x lies between x1 and x2? So, this probability is equal to Fx of x2 minus Fx of x1. So, we have discussed CDF, which is a complete description of the random variables. We may have simpler description. For example, in the case of discrete random variables, we have the probability mass function. A discrete random variable x with the range, because discrete means its range is only discrete points, comprises of discrete points. So, such a random variable is completely specified by the probability mass function. What is the probability mass function? That is, we use the symbol small px of x, that is equal to probability that those s such that xs is equal to small x. So, that is equal to, we write it in simple notation, probability that x is equal to small x. So, since probability mass represents a probability function, therefore, clearly we get summation px of x over x belonging to Rx is equal to 1. If we sum up all the probability mass function, this sum must be equal to 1. We can give an example: binomial random variable. All random variables have specific symbol. This is bi and p, binomial random variable with parameter n and p. So, the probability mass function is described by small px of x, that is equal to n cx p to the power x into 1 minus p to the power n minus x for x equal to 0, 1 up to n. So, here we have plotted the PMF curve for p is equal to 0. It is a binomial random variable with p is equal to 0.8 and n is equal to 6. So, this is the plot. So, that way we can describe a discrete random variable in terms of probability mass function. Next, continuous random variable and probability density function, PDF. For a continuous random variable x, the CDF Fx of x can be expressed as the integral. This is the basic result, that CDF Fx of x can be expressed as the integral from minus infinity to x of Fx u du. Now, this quantity Fx of x is a non-negative function, and it is called the probability density function, PDF. If fx of x is differentiable, we can write PDF small fx of x derivative of CDF of x, ddx of capital Fx of x. So, if the CDF is a differentiable curve, in that case we can find out the PDF as a derivative of the CDF. And also we note that integration of, because if I put a minus infinity and infinity here, this will be infinity and that is equal to 1. So, that way integration of the PDF over the entire range from minus infinity to infinity is equal to 1. We will give an example, Gaussian random variable or normal random variable. This random variable is the most important continuous random variable, and it is described by two parameters mu and sigma square, and the PDF is given by this expression. Small fx of x PDF at point x is e to the power minus this quadratic x minus mu by sigma whole square divided by 2, and this term is normalized because it is a PDF, normalized by root over 2 pi into sigma. So, this distribution occurs in many practical situations naturally, and we denote the normal distribution by x distributed as normal with parameters mu and sigma square. Here is a plot of this PDF. It is a bell shaped curve, and the parameter sigma will determine the extent of this distribution, and mu is the central point, that is this is the mean or even mode of this curve or median of this curve is given by mu. So, we have defined a single random variable and how to characterize this random variable in terms of CDF, and if it is continuous in terms of PDF, and if it is discrete in terms of PMF. Now, let us go to multiple random variables. Suppose two random variables x and y are defined on the same sample space S. In other words, xs and ys are two functions defined from S to the real line. As usual, the argument S is omitted. Now, x and y are called joint random variables. We may also represent a joint random variable as a two-dimensional vector. We can, this is the vector notation. Usually vectors are represented by a column matrix, and here two component x and y. We can extend the above definition of two random variables to any dimension, particularly n random variables x1, x2 up to xn define an n-dimensional joint random variable or n-dimensional random vector denoted by x is equal to these are the components x1, x2 up to xn. This is a random vector with component x1, x2 up to xn. Now, how to characterize multiple random variables? We have the joint CDF. The joint CDF of x and y denoted by, this is the notation, capital Fxy at point xy is defined as, how do we define? This is the probability that S, probability of those S for which xs is less than equal to small x and ys is less than equal to small y. This comma in fact means and we can write this in terms of this intersection event, probability of the event S such that xs is less than equal to small x, intersection S such that ys is less than equal to small y. So, this is the definition of joint CDF, and this joint CDF completely describes two random variables x and y. Now, if we see f x y at minus infinity y, that is the intersection of this event s such that x s is less than equal to minus infinity and s such that y s is less than equal to y. And since this part is phi, therefore, this intersection will be equal to phi and therefore, corresponding probability will be equal to 0. So, joint CDF at minus infinity y is equal to 0. Similarly, joint CDF at x minus infinity equal to joint CDF at minus infinity minus infinity is equal to 0. Also, we can show that joint CDF at infinity infinity is equal to 1. As I said, the joint CDF completely describe two random variables x and y, and we can determine any probability involving x and y using this CDF. Particularly, if we consider f x y at point x infinity, by definition this is equal to probability of s such that x s is less than equal to small x and y s is less than equal to infinity. This y s less than equal to infinity, it will correspond to the sample space. Therefore, we will get probability of s such that x s is less than equal to small x intersection with the sample space, and this will be any event. If we intersect with s, you will get that event only. Therefore, it will be probability of s such that x s is less than equal to small x and which is equal to CDF of x at point small x. So, therefore, from the joint CDF we can find out the individual CDF f x of x, and it is called the marginal CDF. So, the marginal CDF can be obtained from the joint CDF. Joint PDF. Now, we will go to continuous random variables. If the joint CDF is continuous, then it can be expressed in terms of the joint PDF. This is the basic expression. The joint CDF can be expressed as the double integral minus infinity to x and minus infinity to y of small f x y u v dv du. So, this is the relating expression between the CDF and the PDF, and this PDF joint PDF is a non-negative quantity, and if suppose CDF has the partial derivatives, then we can write the joint PDF at point x y as the second order mixed partial derivative del square del x del y of the CDF at point x y. Thus, two continuous random variables x and y can be represented in terms of their joint PDF small f x of y at point x y defined by this relationship. Similarly, for discrete random variables x and y, we can define joint probability mass function, and it is denoted by small p x y at point x y. So, same definition of suppose probability mass function can be extended to 2 dimension and to get the joint probability mass function. Now, as I said, joint CDF or joint PDF is a complete description of two random variables, and from the joint CDF we can get the individual CDF, individual PDF and so on. For example, f x of x, that is the CDF of x, and we showed that it is equal to joint CDF of x y at point x infinity, and if we write in terms of the PDF, this will be the integral minus infinity to x, and since it is infinity, integral from minus infinity to infinity of this PDF of the PDF. So, this is equal to the joint CDF of xy at x infinity, and which is the double integral from minus infinity to x and y infinity, therefore minus infinity to infinity of fxy, that is the PDF at point uy dy du. This is the expression for the CDF fx of x. Now, also CDF fx of x has this expression. This is the integration from minus infinity to x of the PDF at point u du. So, therefore, if we compare this expression and this expression, then this bracketed term must be equal to fx of u. Thus, CDF fx of x is given by integration from minus infinity to infinity, here minus infinity to infinity of the joint PDF with respect to dy. So, if we have to find out fx of x, PDF at point x, then it is the integration of the joint PDF with respect to the other random variable y. Similarly, if we have to find out the PDF of y, in that case it will be the integration with respect to x. So, that way marginal density functions can be obtained from the joint density functions. Now, let us go to a more general case, joint CDF of n random variables. The CDF of a random vector x denoted by x1, x2 up to xn is defined as the joint CDF. This is a CDF because we are considering a random vector single quantity as the joint CDF of x1, x2 up to xn, and given by this is the expression joint CDF at point x1, x2 up to xn, and this is the CDF of the random vector, and this is by definition probability that x1 is less than equal to small x1, x2 is less than equal to small x2, and up to xn is less than equal to small xn. So, this is the joint event, and probability of this joint event is the joint CDF. Like in the two dimensional case, the joint CDF is the complete description of random variable x1, x2 up to xn, and we can get the CDF of any sub collection of random variables from this set. For example, if we have to find out only CDF of x1, so this is the joint CDF at point x1 and rest of the point at infinity. Similarly, if we have to find out the joint CDF of x1, x2 at point small x1, x2, then this is the n dimensional CDF at point x1, x2 and rest of the points at. In this way, we can find out the joint CDF of any order. If the joint CDF at point x1, x2 up to xn has the partial derivatives, then the joint PDF, now we can define the joint PDF, can be written as this is the symbol small f x1, x2 up to xn at point x1, x2 up to xn, and this is the PDF of the random vector at point small x vector, and this is the nth order mixed partial derivative del n, del x1, del x2 up to del xn of the CDF. In this way, we can relate the PDF and the CDF of multiple random variables. Independent random variables. We know what are independent events. The same definition is generalized here. X and y are independent if the joint CDF at point xy is equal to fx of x into fy of y. This is true for all xy belonging to R2. So, that way this definition is a very strict definition, because this relationship should be valid at every pair of point xy belonging to R2. Or equivalently, in terms of PDF, joint PDF is the product of marginal PDF. This definition of independent random variables can be extended to n random variables. In that case, n dimensional CDF will be the product of n marginal CDFs, and n dimensional PDF will be the product of n marginal PDFs. So, we have seen how to characterize random variables in terms of their CDF, PDF, PMFs, or in the case of multiple random variables in terms of joint CDFs, joint PMF and joint PDFs. Next, we will be discussing how to partially represent a random variable in terms of expectation operation. Suppose y is equal to gx is a real valued function of a random variable x. Then e of gx is defined by this integral gx into CDF PDF of x dx if x is continuous, and this is a summation if x is discrete. So, in the case of discrete, summation over x of gx into PMF of x. Particularly, if gx equal to x, we have gx is equal to x, then we have ex is equal to, that is called the mean mu x, and this is by definition this is equal to integral minus infinity to infinity x fx of x dx if x is continuous, and summation over x of x px of x if x is discrete. So, we know what is a mean of a random variable. We also define the moments of random variables. Moments and central moment we will be defining. For a positive integer n, the nth moment and the nth central moment of a random variable x is defined by the following relation: e of x to the power n, that is the nth moment, and I know the definition of expectation. So, this will be integration minus infinity to infinity x to the power n PDF of x into dx. Similarly, central moment, that is the nth order moment about the mean. So, we have to consider e of x minus mu x to the power n. So, that way we will get the central moment, and particularly these moments are important for us. Mu x, that is the first order moment, that is equal to Ex, mean square value E of x square, and similarly variance is sigma x square, that is E of x minus mu x whole square, and this is also equal to, we can use the property of expectation and establish that this is equal to E of x square minus E of x whole square. Similarly, in the case of multiple random variables, for example, joint random variables x and y, we can define the joint moment of order m plus n, and this is given by E of x to the power m into y to the power n. You are taking the mth power of x into nth power of y and then taking the average value, and this is given by this integral. Particularly, if m is equal to 1 and n is equal to 1, we have the second order moment E of x y. So, here it will be x y and multiplied by the joint PDF, and you will integrate from minus infinity to infinity. The second order moment E of x y, it is also called the correlation between x and y. So, now we can define the second order central moment, that is the covariance of x and y, and it is defined as covariance of x y is equal to E of x minus mu x into y minus mu y, and it can be shown that this is equal to E of x y minus mu x into mu y. This is the covariance of random variable x and y. Now, covariance is a very important operation, and it leads us to the definition of uncorrelated random variables. X and y are called uncorrelated if covariance of x y is equal to 0, or equivalently E of x y is equal to mu x into mu y. So, this is a relationship, or this is a definition in terms of the average value. Unlike independence, which is defined in terms of PDF or CDF, here uncorrelatedness is defined in terms of covariance, which is an average value. So, that way this definition is more relaxed, and it has lot of importance in any signal processing application. And also we can show that if random variables are independent, then they will be uncorrelated, but the converse is not generally true. Now, let us see how to characterize random vectors in terms of mean, correlation and covariance. So, for random vector x, this is the random vector, we define the mean mu x is again a vector, and its components are individual mean. So, mu x is a vector consisting of ex1, ex2 up to exn. And correlation, now in the case of two random variables we can find out correlation. Now, since there are n random variables, we have the correlation matrix. So, how to get the matrix? So, we multiply x by x transpose, and then we will take the expectation of the individual components. So, that way the diagonal elements will be the mean square value E of x1 square, E of x2 square, like that E of xn square. This is E of xn square, and the off diagonal elements will give the correlation E of x1 x2. Similarly, this is E of x2 x1. Similarly, we can define the covariance matrix. Covariance matrix, again to get the matrix, we have x minus mu x vector into x minus mu x vector transpose, and then we will take the expectation of the individual terms. So, that way we get a matrix with diagonal elements as the variances, variance of x1 here, variance of x2 here, here variance of xn, and off diagonal elements are the covariance values. So, that way we get the, in the case of multiple random variables, the correlation structure can be expressed succinctly in terms of the correlation matrix and the covariance matrix. We will define jointly Gaussian random variables. X and y are jointly Gaussian random variables distributed as normal with parameters mu 1, mu 2, sigma 1 square, sigma 2 square, rho. And the joint PDF is given by this expression. It is exponential with negative quadratics in x and y, and there is a normalizing factor 2 pi sigma 1 sigma 2 into root over 1 minus rho square. And thus, this joint Gaussian PDF is determined by 5 parameters, means mu 1 and mu 2. It can be shown that mu 1 is the mean of x and mu 2 is the mean of y. Variances sigma 1 square, sigma 2 square. Sigma 1 square is the variance of x and sigma 2 square is the variance of y. And the correlation coefficient rho, that is covariance of xy divided by sigma x into sigma y. In this case, it is sigma 1 into sigma 2. So, these 5 parameters describe the jointly Gaussian random variables x and y. We can also define the Gaussian random vector x. It is distributed as normal with parameter mu vector, mean vector, and the covariance matrix. So, if suppose this is the random vector and mean is mu x and the covariance matrix is Cx, then this is the expression for the joint Gaussian PDF, and this is again this is x minus exponential minus half of x minus mu x transpose Cx inverse. This Cx inverse is the inverse of the covariance matrix into x minus mu x. And now normalizing factor is root over 2 pi to the power n into determinant of the matrix Cx. Cx is a matrix and we can find the determinant of Cx. So, that way this is the joint Gaussian PDF of n random variables. We have characterized multiple random variables in terms of joint CDF, joint PDF, joint PMF, etc. Now, let us see how to describe the conditional probabilities. Suppose if x and y are continuous random variables, then the conditional density function of y given x is equal to small x is given by this. This is the conditional PDF of y given x, and this is a joint PDF divided by the marginal PDF at point x. Of course, we need the condition that fx of x not equal to 0. Fx of x not equal to 0. Similarly, if x and y are discrete random variables, then the probability mass function of y given x is equal to small x is given by this expression. This is the conditional probability mass function. Again, this is the ratio of the joint probability mass function divided by the marginal probability mass function. And we can use this definition of conditional PDF to derive the Bayes rule for continuous random variable, and this is given by f y given x at point y given small x. That is, by definition, this is the joint PDF of x y divided by the marginal PDF of y. And now, if we can write joint PDF in terms of conditional PDF, we will get the numerator, and again this marginal PDF can be written in terms of the joint PDF, and this is given by this. So, that way we get the Bayes rule for continuous random variables. With the definition of conditional PDF and conditional PMF, we can also get the conditional expectation. The conditional expectation of y given x is equal to small x is defined by E of y given x is equal to small x. We are finding out the conditional expectation of y given x is equal to small x. So, this is defined by this integral in the case of continuous random variables. This is the integration, it is expectation with respect to y. Therefore, it is integration of y multiplied by the conditional PDF, and then you integrate with respect to dy. Similarly, this, if we have to take the sum in the case of discrete random variable, this is y multiplied by the probability mass function of y given that x is equal to small x. So, that way we can determine the conditional PMF, we can determine the conditional expectation, and it has importance in estimation theory, because this conditional expectation gives the optimal prediction of y given x is equal to x. What is optimal, we have to explain further, and therefore, it is very important in estimation theory. Let us summarize what we have done today. We defined probability using 3 axioms, then we defined conditional probability by this expression. Conditional probability of B given A is equal to probability of A intersection B divided by PA. Events A and B are independent if and only if probability of A intersection B is equal to PA into PB, and finally, in the probability case we define the Bayes rule by this relationship. This is the posterior probability, and it can be found in terms of the prior probabilities, probability of AK into probability of B given AK divided by sum of I going from 1 to n of PAI into probability of B given AI. This is the expression we obtained through total probability theorem. We also noted that a random variable x is characterized by CDF fx of x, that is defined by probability of those sample point for which xs is less than or equal to small x. Similarly, we define probability mass function, probability of S such that xs is equal to small x, and this is for discrete case. Similarly, we define the PDF, probability density function. It is given by this expression. We also noted that joint random variables x and y are characterized by joint CDF and joint PMF and joint PDF. These are the corresponding functions. We have defined joint CDF, joint PMF and joint PDF. And we introduced one very important concept: x and y are independent if and only if the joint CDF is equal to product of marginal CDF for all x y belonging to R2. Similarly, the same can be defined in terms of joint PDF. Joint PDF is the product of the marginal PDF for all x y belonging to R2. So, this is the definition of independent random variables. X and y will be independent if joint CDF is product of marginal CDF, or equivalently joint PDF is the product of marginal PDF. We define the expectation of the function by this relationship. E of gx is integration from minus infinity to infinity of gx fx of x dx. Then correlation of xy is given by E of xy, covariance of xy is given by E of x minus mu x into y minus mu y. We define what is correlation, what is covariance. For a random vector x, the correlation matrix Rx and the covariance matrix, correlation matrix Rx is equal to E of x transpose, and the covariance matrix Cx is equal to x minus mu x into x minus mu x transpose. These are the description of correlation structure in the case of random vectors. And we introduced the n-dimensional Gaussian random vectors, which is given by x. It is a normal distribution with mean mu vector and covariance Cx matrix, and this is the PDF of the Gaussian random vector. The conditional PDF and the conditional PMF are used to define the conditional expectation. Finally, we define the conditional expectation E of y given x is equal to small x. It can be defined in terms of the conditional PDF and conditional PMF. In the next lecture, we will discuss the linear algebra of random variables. Thank you.